Alright, kiddos, let's see if we can get this to work. You don't want me breathing on you today, so that's why I'm not there in school. But we can't fall behind, so I still wanted you to at least start seeing section 9.4. We can finish it Wednesday when I make it back, which will be tomorrow for you guys. When you're listening to this, there are 2 tests in section 9.4. I'll see how long this recording takes, and maybe if there's time, I'll have you see both tests. But we're starting off just with the direct comparison test, and that's what you can see right here. This is going to be an endeavor, but sadly, since I'm not there, I don't have you guys to ask as to what number we're on, and I don't remember, so I'm just going to leave it blank for right now, and you guys can fill it in. But this is going to be an endeavor. It's our next test. So far, what have we done? We've done geometric series test. We've done nth term divergence test. We've done integral test and p-series test. So now we're on the direct comparison test. There are a couple weird things with this test. Let's just go ahead and start off looking at it. So if you guys start reading with me, or you're probably hopefully already writing this, by the way, if I'm going too fast at any point, feel free to ask whoever's subbing for me just to pause this until you catch up writing down whatever you need to. Because I'm not there, so I can't quite tell how you guys are doing with writing things down. But as you guys are writing down the direct comparison test, there are a few conditions at the very beginning. Remember, conditions we can see with the if. So we have here right in the beginning, if 2 different sums, a sub k, b sub k, just shows they're different, right? With positive terms, that's a big one. With positive terms, such that each term in the sum of a sub k is less than its corresponding term in the sum of b sub k. So if you're on the third term of this one, it better be less than the third term of that one, or the fourth term, with the fourth term, fifth term, that's all the corresponding thing means. Those are our conditions. Now, there are going to be some funny ins and outs of those conditions, but that's okay. Let's go ahead and keep reading and just see what we are able to tell. If the bigger one converges, then the smaller one will converge also. One way of remembering that is bigger. If you can prove bigger converges, then you can prove the smaller converges also, BC. I kind of remember it a different way, but either way. Then, and I'll show you that down here below. Then the second, if the smaller diverges, if the smaller of the 2 diverges, then the bigger will diverge also. Now, if you keep reading, use this test as a last resort. Other tests are usually easier to apply. Now, we haven't learned all the other tests, right? This is just the next one in the series that we should, I shouldn't say series, in the progression that we're learning in Chapter 9 of all the different tests. But as remember, at the end of this chapter, at the end of, I think it's section 9.6 will be our next test, or our full test on 9.1 to 9.6, you're going to want to try each of these tests. And direct comparison is one that is useful, but it's also kind of hard to figure out. So that's why it just says use it as a last resort. This isn't going to be like the nth term or like geometric or like p-series that are really fast to use. It's kind of harder to see. And also, just a quick reminder down here, it's only for series with positive terms. If it's negative, or if it flip-flops, if it alternates, then we're not going to be able to use this test at all. It could start off negative, possibly, and then go positive for the rest of the time to infinity. And if it does that, there is something we can do to deal with that, but that's on the next page. Let's look down really quickly at how I like to remember it. Of course, another quick reminder, only works for series with positive terms. However, up here it was showing you the ways of remembering if the bigger converges, smaller. So if you can prove bigger converges, then you can prove smaller converges. And then if the smaller diverges, SD. The way I like to think about it is for converging, if you can prove that the bigger one converges, you can like squeeze in the smaller one, because converging, right, is getting closer and closer and closer to. And if you're talking about series, then the partial sums are getting closer and closer and closer to. So if the bigger one is getting closer and closer, then it's going to squeeze in the smaller one, and the smaller one's going to get closer and closer and closer as well. Diverging, if the smaller one is diverging, then it's not getting closer and closer, right? It's like going, I don't know, to infinity or something like that. The partial sums are going to positive or negative infinity. So if the smaller one is going to infinity, then it's going to push out one that's above it to infinity as well. So if I can prove the smaller one pushes out, then it's going to push out a bigger one. I don't know. I'll try to explain this a little bit better, or at least help you visualize it a little bit better when I get in, because I'm doing all these hand motions that you guys can't see right now. But whether you think of it like up here, where it's with BC and SD, or whether you think of it as the smaller one pushing out will diverging will make the bigger one diverge, and a bigger one squeezing in, or converging, making the smaller one converge. However you remember it, we just need to remember what happens based on the comparison of one with another. Let me go over a quick note real quick before we see some examples. A quick note, and up here you can look on the actual page number. It explains it maybe a little bit more in depth than I'm going to do right now. But here's the actual verbiage that it uses in the book. And I'm going to try and just kind of show it to you. It actually, Ethan will recall this if he's there. There was something with the integral test where it says if it's positive, continuous, and decreasing. And there were just a few that don't actually decrease right away, but then after a couple terms they keep from then on out, from then to infinity or the infinite terms, it does end up decreasing. And there was a way for us to technically deal with that. We'll probably peek at that once I get back. But kind of the same thing applies here. What you needed to know for some of those funny ones in section 9.3 is included in this note. It says, because the convergence of a series is not dependent on its first several terms. The convergence of a series. So the first few terms are never going to cause us problems, because we could always separate the first few from the last, which means I could take like the first, or the first and second, or the first, second, and third, and then just add whatever n I stop off at all the way up to infinity. I can separate. I don't have to keep it from 1 to infinity, or from 0 to infinity, or from 2 to infinity. I can split these things up. So because the convergence, so here's something that we haven't really seen, the convergence of a series is not dependent on its first several terms. You could modify the test to require only that one of the series terms has to be less than or equal to the other one for all n greater than some actual integer. What that means is, well, let me show you a visual. If I was to give you something, for instance, like, here, I'll just do one of these. Now I'm giving you a graph, which is going to be kind of funky, but I'm just trying to show you like different terms. And if I was to give you something like, let's go with like a cubic function. And then if I was to give you something like a linear function. And I'm not actually defining these, but I'm just calling one. This could be, remember we can make functions like from the actual term formulas. So if I were to call this one like b of x, which would be like b of n, but b of x instead. And then if I was to call this one like a of x, according to our direct comparison test over here, b is supposed to be the bigger one, and a is supposed to be the lesser one. It tells us, okay, one's supposed to be bigger, one's supposed to be smaller. Now, if you look at this graph of the functions right here, right? And okay, I didn't quite highlight that quite well enough. Let's do it right here. Right here, b of x is not always higher than, actually, you know what, guys? I totally switched that around, didn't I? Hold on, b of x is supposed to be the higher one. I mislabeled this because, let me show you what I mean. B of x is higher for little bits and pieces right here. But think about, you're trying to go to infinity, right? So if I'm going to infinity, even though b of x right here is higher, as I go to infinity, well, from here on out, it's going to be lower. So actually, this one is my a of x. This actually kind of proves the point. And here, even though b of x is lower right there, as I go to infinity once again, it's going to be higher from here on out, right? And if I'm thinking about specifically, sums don't ever really go from like negative numbers, right? It doesn't go to negative infinity. Sums always go from 0 to positive infinity, 1 to positive infinity. I wouldn't really have to worry about any of this, right? But I would have to worry about this. Let's say the intersection point right here where all the problems happen. Let's say that that's like at n equals or x equals 1. So if I was worried about the summations, and if I was looking at them, I could just, what this little note is basically saying, I could split up the sum, which maybe would go like normal, right, from n equals 0 to infinity of my a of k, or of my b sub k. And I guess it wouldn't be k in this case because I used n. So it'd be like a sub n or b sub n. And I could split this up, and I could say, you know what, instead I could talk about this from, well, where does this theorem hold true? Well, this theorem holds true on this interval to infinity. So I could say, all right, you know what, from 1 to infinity, this is totally fine, right? But I need to make sure that it equals this initial one. So I need to say plus a sub 0. So I could say, okay, you know, a sub 0 plus a sub 1 plus a sub 2 plus, and I could split it up. I could take it out of the summation itself and then say, you know what, this one now fits that whole qualification of needing to be lower than, according up here, right? Lower than b sub n or b sub k or b sub b of x or whatever you want to say. Just kind of the idea of, once again, yes, this condition does need to be true, that you have a of k less than its corresponding term in b sub k, but that doesn't mean that I have to keep it like it is originally given to me. I can split it up to be the terms that don't fit the qualification, like here where I had, you know, the one that was higher than the other. I could take that separate, and I could just look at the actual parts that do work, as long as it still goes to infinity. As long as it still goes to infinity. Let's go ahead and go peek at some examples of the direct comparison test, okay? So, first of all, if you can see the first example here, determine if the series converges or diverges. And if you're looking at this, remember, we're always thinking about all of our tests, not just the one that we're learning. If we were to look at this one right here, okay, could we see it as a geometric series? Well, we could go ahead and start writing terms, right? And we could say, okay, when n is 1, I would have 1 over 2 to the 1 plus 1. That'd be 1/3 plus, next term, 1 over 2 squared plus 1. So that'd be 1/5, right? And then I could say plus, if n is 3, that'd be 1 over 8 plus 1, so 1/9. Oops, I can't write my 9s. And I could do another one. Okay, but if we look at this, you guys can probably tell there's no common ratio in these, right? Okay, so I know it's not geometric. Now, are these terms, let's see, is this a p series? No, it's not a p series because it's not n raised to a power. It's not 1 over n squared. It's 1 over 2 to the n plus 1. It's not a p series. I could think the nth term test, but the limit as n goes to infinity of 1 over 2n plus 1, well, that equals 0, so we know nothing, right? So that doesn't really help. What else did we learn last chapter? Or not last chapter, but sections 9.1 and 9.3. It's not geometric. We know nothing from the nth term test. Oh, integral test. It wasn't P series. Integral test. Okay, well, we could say, you know what? Hold on, look at these terms, right? They're positive, it's continuous, it's decreasing. So, of course, let's use integral test, but the dilemma is, let me clear off some of this work. Did any of you guys see a dilemma with this in the integral test? If we were to try to take the integral of 1 over 2 to the n plus 1, well, we would make it into x, right, dx. And I would make it from 1 to b, the limit as b goes to infinity. How do we take that integral, right? I could maybe try to make u 2 to the x plus 1. But problem, right? If I go to take du, I need another 2 to the x and then the ln of 2. Well, I can deal with that by dividing to the other side. But the problem is I don't have a 2 to the x to go with that dx. The integral test would be hard, if not impossible. So that's not a good one. Remember, the integral test is only good if I can take the integral itself. So then we come to our comparison test. If you guys look at this sum of this summation of these terms, this is going to take some practice. It's definitely going to take some practice. But if we were to look at the series from n equals 1 to infinity of 1 over 2 to the n. They might be like, did you just pull that out of thin air? Well, no. A, I knew what to compare it to because I've had practice on them. And B, well, I'm trying to look for something that's similar and yet either bigger and converging or smaller and diverging for BC or SD, or bigger squishing in or smaller pushing out. If you look at this one, that we were given 1 over 2n plus 1, well, what's that close to? Well, that's close to 1 over 2n. Why is that so much better? Well, I'll explain it in just one second, but first of all, can you guys tell how these two are related? Which one's the bigger, which one's the smaller? We have to make that, I'm going to show it with an inequality, but we have to make that conclusion in order to be able to apply our test. So if you were to look at each of these, you could write out terms for each of them and try to look at it that way, or you could just try to use your mathematical sense. And you could say, well, hold on, 1 over 2n plus 1, that denominator is going to be a little bit bigger every time. Well, if the denominator is going to be a little bit bigger every time, the numbers are going to be a little bit smaller every time. So therefore, it's less than. So I have my bigger here, right? And then I have my smaller here. I have my bigger and I have my smaller. So what I'm trying to do, if it's easy enough, is in this case, if it's my bigger, I'm trying to use the squeeze in idea. I'm trying to say, okay, hold on, if I have a bigger, if I can just show that this bigger one converges, then it's going to squish in the smaller one and show me or prove that's going to be convergent as well. Now, how do I do that? Well, let's look at this for just a second, the one that we compared it to. If I was to look at the series from n equals 1 to infinity. Why is this so much nicer than the other one? Well, it's nicer because, let me see if I can get this to right, there we go, 1 over 2 to the n. If I look at 1 over 2 to the n, this is a lot nicer because this one, if you actually started expanding terms, 1 over 2 to the 1, so 1 over 2, 1 over 4, 1 over 8, 1 over 16, what are those? Wait a minute, that looks like a geometric series. So if I just look at this one, it's a geometric series. Not only is it a geometric series, but it's a geometric series with r equals 2. If you were to expand it out, r equals to 1/2. Well, why is that nice? That's nice because since 1/2, if you guys are remembering, I'm writing all kinds of funny things down here. Since 1/2 is in between 1 and -1, It's a geometric series, therefore the series converges, right? Without going too in depth about all of our writing, etc., etc. So since I can say that this one converges, since I can say the comparing one that I'm comparing it to converges, then I can say, all right, cool. By the comparison test, and I'm going to change this a little bit because there actually are a couple different comparison tests. So by direct comparison test, since the bigger series converges, since the bigger one converges, it's going to like squish in the smaller one. Since the bigger one converges, the smaller converges also. Check. Okay? This is how the direct comparison test works. I have an original series for whom geometric series doesn't work, and p series doesn't work, and nth term doesn't work, and integral, how do I take that integral? But there's one that's really, really close to it that does converge or diverge, and if it's bigger, I need it to converge to be able to prove anything, and if it's smaller, I need it to diverge to compare anything, or else I wouldn't be able to use it. I know it's kind of weird. It might seem like I literally pulled it out of thin air, but I didn't. It's more of a strategy as to how to choose these. Let's try with another one and see if we can kind of get more of a hang of it. So if we were to, I think I have 3 examples total. If we were to look at the next one, I have this series right here from 1 to infinity. Okay, so we have 3 over n plus root n. Whenever you have n plus root n, once again, you could look at this, you could expand the terms, it's not geometric. Take the limit as n goes to infinity, it ends up equaling 0, we know nothing. Integral test, if I try to take the integral of this from 1 to b as b goes to infinity, I'm proving a point. You would have 3 over, well, how would you take this integral, right? I didn't change those to x's. I keep on doing that. Dx. You would make, what, u equals x plus root x, because remember, we can't split up those denominators, right? But then my du, you can imagine, would be 1 plus, well, bring down the 1/2. That doesn't look so hot, right? Because I don't have anything even like that back here in order to think about with my u sub how to make that work. So once again, the integral is very difficult, if not impossible to find. So then we have to think about, okay, how can I compare this? Because none of my other tests have worked so far. How do I compare this, or what do I compare this to? If you think about up here, back when we did it up above, when we were doing this one up here, I tried to take what I was given and simplify it. 1 over 2n plus 1 became just 1 over 2 to the n. I'm going to do the same thing here as well. Now, once again, we could choose the wrong thing, and then we weren't or wouldn't be able to make any conclusion by direct comparison test. So some of it's trial and error, seeing if you can pick the right one. But just because I'm doing examples, let me show you. N plus root n, well, that's a mess, right? But what if we just did n plus n? N plus n. Now, n plus n, you're like, seriously, how did you? Okay, well, n plus root n was really difficult because I couldn't combine those two. So root n compared to n. Now, wait, what would the comparison be? Well, the comparison, if I'm thinking about 3 plus n over root n, well, root n is going to always be smaller from 1 to infinity. It's always going to be smaller than just n plus n, right? So if the denominator is always going to be smaller, the number will always be a little bigger. So really in this one, it's going to be greater than, not less than. Now, greater than, not less than, well, that kind of, you could think is a dilemma. But remember, with our direct comparison test, it's not just if it's smaller. We also sometimes can, meaning that the one that we're given doesn't always have to be smaller, because sometimes it can be a bigger one squishing in, or it could be a smaller one pushing out. So let's go ahead and come back to our example if I can get back there. There we go. All right, what was so helpful? What is so helpful about this comparison series? Well, let's take them off to the side and let's think about them, just like we did the other one. If I was to think about n equals 1 to infinity of 3 over n plus n, well, that's a mess. Let's do 3 over 2 times n. From our properties, we could go ahead and say, well, we can pull a constant out. Not that we necessarily need to, but he might help you look at them a little bit differently. Pull out the constant, and now I have 1 over n. Well, okay, hold on. Can I figure out the convergence or divergence of this one? Well, geometric series, no, because it'd be 1/2, 1/3, 1/4. Nth term test, limit as n goes to infinity is 0, no, nothing. Integral test, well, I probably could, but p-series test would be even easier, because p-series says 1 over n to a power, and his power would be 1, right? And so that's a really messy one. If I have 1 over n to the 1, what does that mean? Well, p-series test. P is equal to 1. Well, what does that tell me? Well, hopefully you remember that in a p-series test, since as long as p is a real number, which it is, p is equal to 1, if I have any power that is less than or equal to 1 and greater than 0, what does that mean? The series diverges, right? Why is that helpful? Well, because if you look back up here, in our original, he's smaller. And if the smaller diverges, then the bigger diverges, or smaller is going to push out. So if the smaller pushes out to diverge, he's going to push out the bigger one as well. So how can we put this in words? Well, we would say, let's set him off to the side real quick, just because he was super important. I'm going to go ahead and state with my direct comparison test. So then by the direct comparison test, since the smaller series which was the one we were comparing it to, n equals 1 to infinity of 3 over n plus n. So my punctuation is a little funny up here. Okay. Since the smaller series diverges, then the bigger series, which was the one we were trying to figure something out about, which was n equals 1 to infinity of 3 over n plus root n, diverges as well. I'll say also just to mimic like up above. So if you look at each of these examples, in each of these I was taking the one I was given and I was simplifying it in a sense, but in one that was very strategic in that I was able to, with a quick test off to the side, I was able to determine whether he was converging or diverging. Same thing down here. I tried to kind of simplify him because the way he was originally would be too hard with, or even impossible with any of my other tests. But with the comparison one, well, I was able to figure out something quite quickly. Let's do one more example, our last one. Here he is. I have n equals 1 to infinity of sine squared of n over 2n, 2 to the n, sorry. You guys can probably, even just by looking at this, think the integral test, no way, Jose, right? Nth term test, you might be like, I'm not so sure about nth term test. Maybe it would work, but nth term test, if I took the limit as n goes to infinity, who's stronger? Sine squared of n or 2 to the n? Well, sine squared of n, sine squared can only go between negative 1 and 1, right? And negative 1 to 1 squared, that's not going to get me very high. Whereas 2 to the n is going to be increasing, yeah. Pretty sure this just equals 0. So then we know nothing. That's not very helpful, right? Integral test is out. Nth term test is out. Geometric series, nah, not feeling it, right? It's not even 1 to begin with. So then let's see if we can compare it. Now, I just said a second ago, sine squared of n is only going to go between 1 and negative 1, right? So if it only goes between 1 and negative 1, more specifically, actually, sine squared, a negative times a negative is a positive. It's going to go between like 0 and 1. Well, what if then I was just to compare it to 1 over 2 to the n? Now, we just looked at this a second ago in the sense of this is going to be super nice off to the side, right? Because if I was to, just like we did a second ago, if I was to take this series n equals 1 to infinity of 1 over, let's see if I can get my infinity, there we go, of 1 over 2 to the n, that's the same thing as 1 over 2 to the n. I could see this just as geometric series, where r is equal to 1/2. And since 1/2 is in between negative 1 to 1, the series converges. But hold on, this is only going to help me, right? This whole rationale off to the side, converging. The only way I can prove anything with direct comparison test and converging is if the bigger one converges. Well, hold on, is this always bigger? Well, looking at my two series that I'm trying to compare, sine squared of n over 2 to the n and then 1 over 2 to the n. Well, if we think about sine squared, right? Sine squared, if I think about when sine is 1/2, 1/2 squared is 1/4. When I think about, what's another sine value? Root 3 over 2 squared would be 3 over 4. All of these different values are going to be smaller than 1, which is over here in this one, right? And so then I could say that then the one on the left is smaller than the one on the right. And since I'm able to say that, since I'm able to make that determination, then I can say, perfect. By the direct comparison test, I can once again make a conclusion. Now, once again, if it hadn't been smaller than, then I would have chosen the wrong one, or the one that I thought I could compare it to wouldn't have actually helped. So I would have had to either compare it to something different or say, please let us learn more tests. So as you're getting the hang of this, you're not going to necessarily always have the right comparison that you make, which is why it makes it a little bit more of an adventure, trying to figure out what comparison to make. But we'll figure it out little bit by little bit. What am I trying to say? By direct comparison test. Since the bigger series, which is my summation from n equals 1 to infinity of 1 over 2 to the n converges, then the smaller series, which is the one we were trying to figure out about, n equals 1 to infinity of sine squared of n all over 2 to the n, converges also. Hopefully that gives you guys at least a little bit of a hang of the direct comparison test. I know it's a little weird and you have to be a little creative, but just like the other ones, we'll get the hang of it, and we'll, you have to be, as you can tell, you have to be good at those other tests, right? Like this one here, the geometric series, the nth term, etc., just to be able to make those conclusions. Just like the others, we'll just get the hang of it. So, just in case you guys do have any extra time to class, I meant to have the homework written down here for you. It is online, I believe. I'll make sure that it is. I don't remember what homework number it is, but it is section 9.4. Now remember, there are 2 tests for section 9.4, and we've only seen one of them, so you wouldn't be able to finish it, but you could start it as page 616. The problem numbers are numbers 3 through 21, odds. Once again, having you guys have the odds so that way you can be checking your answers. And then 23 through 30, those ones are all good, so that's an all. There technically are some review questions in this homework. They're not extra credit, they're just review. So you'd have to go back to section 9.1. Remember how these review ones work. Go back to the section. So go back to section 9.1, try number 17, or do number 17, I should say. Section 9.2, do number 45. And then section 9.3, do number 71. It's up to you as to what strategies you do. Once again, you could be doing these review ones first and then going to the new ones, or vice versa. Either way works. But say in this homework, since we didn't get through both tests, you could go ahead and do the review ones first and then start in on page 616. The one test that we didn't get to see, let me remember what that was. The direct comparison test was the one we already did see. The limit comparison test. Section 9.4 is all the comparison tests. So there is direct comparison that you already saw that we talked about, and then the limit comparison we'll talk about when I get back. So that's section 9.4a. You guys be good. Hopefully keep working, and I'll see you when I get back. Bye.